So this is the plan of my talk. First, I will give you a brief introduction to pattern formation and amplitude equation. Then I will talk about the model which I have studied. And then I will tell you about the derivation of amplitude equation using multi-scale analysis. And I will also talk about the stability of amplitude equation. And finally, I will conclude my talk with a summary. So pattern formation. So pattern emerges in specially extended systems in out of equilibrium situation imposed by varying external parameters such as temperature gradient, concentration gradient, or chemical reaction. So here in this picture, I am showing you a top view of the flow pattern of a fluid layer when heated from below. So this type of pattern emerges when the temperature gradient is above a critical value. So here in this picture, I am showing you pattern formation governed by Swift-Hohenberg equation, which has a finite wavelength instability. Here in this picture, I am showing you pattern formation in phase separating binary mixture in presence of chemical reaction. So what is common in these cases are that there is a featureless base state or homogeneous state which undergoes a finite wavelength instability, and above that instability system shows pattern formation, and the main feature of those pattern depends on the nature of instability. Okay, and the pattern so the patterns that emerges from same type of instability exhibit a number of generic feature at the onset of instability, which can be studied using amplitude equation. So this is the pattern. This is the typical pattern which varies rapidly in space as well as in time, whereas this is the amplitude. So basically, amplitude equation describes slow modulation of pattern in space and time just above the onset of instability. So at the onset of instability, so the pattern described by this field phi rt, we can expand it in terms of a amplitude ART and a carrier wave at the onset of instability determined by QC, and so on. So our goal in this talk is to obtain the dynamical equation for ART. So this is the model I have studied. I have studied the generalized active model V, and this is the evolution equation of the order parameter phi rt, which is nothing but the density difference of the two phases, two species A and B. So in addition to the normal phi cube term, we put a generalized, we generalized it by adding a g phi square term, and these are the active current terms. So lambda grad phi square and xi this big term are the current term, active current term. So these are just the strength. So normally this equation shows phase separation. So to induce pattern formation in this equation, what we have done is we have added chemical reaction, reversible chemical reaction of red gamma. Okay. So in presence of this reaction, this is now our evolution equation. We are interested in roll patterns, so we consider one dimension, and this is the evolution equation in one dimension. Okay, so in one dimension we do not have rotational current. However, the strength of the rotation free current reduces to some lambda effective equal to lambda minus xi by 2. Next, we perform stability analysis by perturbing the order parameter with respect to some base state phi 0, and we set phi 0 to be 0. So these are our linearized. This is our linearized evolution equation. We then Fourier decompose it and get a linear dispersion relation of this form. So from this dispersion relation, we get the critical wave number as well as the critical reaction rate. As we see, there is a critical reaction rate QC at which just one mode starts become unstable, and below gamma C we have a band of wave number that become unstable, and we have this expression of Q plus minus like this. So these are the these curves are for these parameters. Okay, so here I am showing you the plot of the order parameter at t equal to 1000 for different values of reaction rate for this set of parameters. So this set of parameter yields gamma C to be 1. So when gamma C is equal to 1, so this phi is actually close to fluctuates around 0. So this is just 0. So below phi C, below gamma C, so we have a finite amplitude of our order parameter, and the spatial modulation is quite sinusoidal in nature. So this indicates that at the onset of instability, so the pattern formation is given by only one wave number or just few wave number around that critical wave number QC. Okay. So to do the multi-scale analysis, first we choose a small parameter epsilon, and it is given by epsilon square equal to gamma C minus gamma by gamma C, and this basically measures the distance of the point of instability at the onset. Okay. Now in terms of epsilon, we rewrite our q plus minus. This is what we end up with, and the width of the unstable mode becomes like proportional to epsilon. From the dispersion relation, we get sigma to be of the order of epsilon square. So using these two information, we write our slow variable capital X equal to epsilon x and t equal to epsilon square t. And then we rewrite our operator like this. And then at the onset, we expand our order parameter in terms of in the power of epsilon as this. So phi 1 is this term. So our goal is to obtain a dynamical equation for AXT as it is the dominant mode at the onset of instability. Okay. So we insert everything into our evolution equation and compare terms of the same order of epsilon. So order of epsilon, we get the linearized dynamical equation, which is obvious, and then order of epsilon square, this is what we end up with. So this gives a relation between the first nonlinear term and the linear term, A and B. Okay. At the order of epsilon cube, this is the first time we get a time derivative of our phi 1, the dominant mode, dominant amplitude. Okay, and after doing this calculation, so lots of term doesn't contribute. For example, this term within the second bracket doesn't contribute. We eventually get a evolution equation for A. Okay, and this is what it look like. So this is our amplitude equation. Now this amplitude equation is supercritical when this term is negative, and it is, we call it subcritical when this is positive. So our condition for subcritical and supercritical transition look like this, and this is our phase diagram in G and lambda minus xi by 2 plane. Okay, it shows that when G is equal to 0, so the transition is always supercritical. However, when G is non-zero, so model parameters determine important role, play important role in determining the nature of instability. So in the next figure here, I am showing you the order parameter in the supercritical regime. So in the supercritical regime, the spatial modulation is quite sinusoidal, whereas in the subcritical regime, it is non-sinusoidal. Okay. We also obtain the amplitude in the for the spatially homogeneous solution. So this is what we end up with. We also calculate numerically the RMS amplitude of the order parameter for this set of parameters. So this gives GC to be 1.275. Below GC, we are in the supercritical regime. So the RMS amplitude of the order parameter increases monotonically as we go away from the point of instability, whereas in the subcritical regime, so there is a discrete jump. Okay. Next we perform the stability of the amplitude equation. So first I perturb the amplitude by writing this form, and this yields R0 square to be of this form. So the amplitude has to be positive. So this gives a band of permitted wave number in which the amplitude equation is stable, or the amplitude is stable. And then I perturb both phase and amplitude. So this gives me a domain of wave number in which my amplitude becomes unstable due to phase modulation. Okay, and it is known as IISc instability. So basically, in case of phase modulation, we will see patterns of different widths in the system. Okay, so this is the conclusion of my talk. So I have obtained derived the amplitude equation for the active model B. So using multi-scale analysis, when G is equal to 0, the instability is always supercritical in nature. When G is non-zero, the model parameter plays significant role in determining transition. And we also obtain the condition for IISc instability, and it is found to be independent of G. So thank you for your attention.
Thank you. We have time for one question.
So in the beginning, you showed the pattern with chemical reactions.
Yes.
Yeah, last one. So there, the concentration takes two possible values, plus A or minus A or some such thing.
Yes.
But in your analysis, there is no saturation effect seen.
Saturation effect seen means? Means here.
Yeah, in this equation, you know, there is no flat top in the curve.
Flat top. Okay. So you have gradient terms. Okay, and then you have a wave number selection. So it is finite width, and then gradient term will smooth those. Yeah. So that is what I can tell you visually, at least. So flat will be when we are far from. So our depth has to be. So here it has to be like gamma C, we have to go far below gamma C to get those flat thing. So this is done at the onset, and the picture I showed is just the general picture. So this amplitude equation is valid near the onset of instability.
Okay, thank you.